Good morning. Thank you so much for coming. This is our series of tech talks for today. This is the first one. It's called Causing Chaos, the Future of Physics and Destruction in Unreal Engine 4. I'm Matthias Worch. I'm a design lead at Epic Games Special Projects, and I'm one of 4 speakers today. I'm going to tell you a little bit about how to build interactive experiences using chaos. Joined by 2 co-workers today. First, we have Jim Van Allen, Senior Technical Artist. He's going to talk about the art of destruction, and Michael Lentine, a lead physics programmer on chaos, will illuminate the tech behind chaos. We're also joined by Jeff Rous from Intel, and he's going to talk a little bit about how we made chaos fast. So chaos is our upcoming physics system, which is going to be the main physics system in Unreal Engine. It's still in active development, so we work on it right now, but there is going to be an early access version of it in 4.23, which is coming out very soon. That's going to have all of the code, as well as some content examples that we used to make the demo that we're showing. Now, chaos is a complete physics system, right? It's going to do everything that you expect a physics system to do in Unreal Engine. Also happens to be really good at destruction. So when we wanted to reveal it to the world at GDC, that's what we created. We created this destruction demo. Now, I hope you've seen it at this point. We showed it at RTL as well yesterday, but I do have a short clip here. Well, I can't get enough of it, so even if you've seen it, hope you like this.
Breaking news. Robo-resistance leader Chaos has broken into a robo-ready research lab and stolen top-secret military hardware. A recall agent has been dispatched.
Okay, Agent 38, it's Renegade recall time. I'm not even sure you hit that one. Good thing it's a bank holiday. She's getting away. Activate rocket boost and get after her. I'm compensating for your lack of skill with higher caliber weaponry. She's on the move again. Get after her. Let's see her teleport out of that one. Now would be a good time to figure out what that thing actually does. Oh, that's not good. On the bright side, you've been approved for mandatory overtime.
All right, so let's start by talking about designing with chaos and how you create interactive experiences around this. The creative behind this demo itself, which you can play, is rather easily explained, right? We wanted to create an homage to old light gun games. So when you're playing this, you actually have 2 Vive controllers and you get to shoot at it. That makes it a lot of fun. So you get to smash up an entire city. And we wanted to make sure that you actually had a goal doing it. So you're going after this little robot called Chaos, or KOS, and you get to use destruction as a tool. So if you want to author something like this, I want to give you a little bit of an idea of what you have to play with. Everything that you've seen, everything that is in this demo was completely created in Unreal Engine. We didn't use any outside tools other than, obviously you go into Photoshop to create textures, etc. But all the destruction tools are actually in Unreal Engine. And the reason I like pointing this out is because it shows you how tightly integrated chaos is with Unreal Engine 4, right? It's actually part of the engine. And we'll come back to that again and again. Everything you see in this demo and that you can play is rendered at real time as well. And we're using a regular high-end gaming PC that you could buy in stores right now. Now, there's a difference between rendering something at real time and actually simulating something at real time. And obviously, everything here is super heavy on simulation. So let's unpack that statement a little bit. Everything that we show you is simulated at real time as well, with one caveat. We only do it when needed. And we're going to go into that a little bit deeper. It gives you a really good idea of how chaos works under the hood. So as I go through the demo that we created, there's 3 distinct sequences. There's the first one, where we're hunting chaos through the streets. And she's trying to hide behind various pillars, and we keep flushing her out. And everything here is 100% real time. We have the entire first section streamed in as well, right? We're not being really creative about it. So we don't know where you're going to shoot. So as we're going past this, all of this is happening 100% at runtime. Then we go over some buildings. We stream out the first section. We stream this one in. And this is where chaos starts hiding inside buildings. So we upgrade our arsenal, and we just start smashing up the entire buildings. And once again, both of these buildings, including Robo-Ready Headquarters, 100% just runtime and real time. We don't do anything special here. And everything here is simulating at runtime. Then we get to the third sequence, which is a little bit different. This is a cutscene at the very end where we're crumbling an entire city block as this huge robot. Somebody told me she's called Mildred. I did not know that. It's like rising and crumbling the entire city block. And this one was actually pre-simulated. So we did this in Chaos, but then we baked this out as a cache, which we're playing back at runtime. Now, even though we're playing back a cache, it doesn't mean that this is not still a dynamic system. And if you understand that a little bit better, I think you have a really good idea of what Chaos is actually doing under the scene, or behind the scenes. So we can, if we want to, actually pre-cache simulation, and we can bake them out. And that's actually really useful to us and to you, because it allows us to art direct something, right? If we have a really good destruction that we don't want to be dynamic, that we want to make sure happens exactly the same time every single time, we can actually do that, and we can pick the perfect one. It also allows us to do mass destruction at performance, because something like that third sequence, where we're crumbling an entire city block, you could not do that at current hardware. So even though we're caching this out, everything that we're doing in a pre-cache simulation is still created using exactly the same tools. It's using the same data type behind the scenes. It's called a geometry collection, which has all of this destruction in it. And what's really cool about Chaos is that even though something is pre-cached, any part of that pre-baked simulation can still become active at any time. So as we're replaying these giant caches, if you now want to make it an interactive experience, for example, by giving the player or any other interactor a weapon, the parts that you start interacting with can become active. And so you might have 10,000 rigid bodies, I'm kind of making up a number, falling down, and that's pre-cached, and it's playing back perfectly at performance, but then you shoot at a small portion of it, and 400 of those actually become active. They start interacting, and they do exactly, they react to every outside stimulus that you would expect. So in Chaos, destruction is never static. This is never a static cache that just plays back exactly the same thing, the same way. It can actually react to anything that you throw at it. Right, so Chaos can react to the dynamic world state, and by doing it, you create something that looks amazing, is incredibly performant, but still can react to everything that you need to at runtime. So if you wanted to create a scene where you put a player at the bottom of this building, for example, but you don't know where the player is actually going to stand, and you want the player to react because there's giant chunks of debris falling down on her, and you give her a weapon and you want her to actually be able to shoot that up, you can do that with Chaos. If this was a completely static, pre-baked simulation which came out of an outside package and you just played that back as an Alembic or something, you couldn't do that. But here, the player can shoot at the specific parts of the simulation which she wants to interact with, and she can crumble that and survive that situation. And that's literally a game changer, because I've been making games for 20 years, and a lot of times, these kind of situations, you have to put the player in a bubble, right? Because you need to know exactly where the player is going to stand, because everything that starts raining down won't be able to interact with it in any shape or form. That's the big difference here. Now, Chaos can do all of this because it's a system. Right? It's a first-class citizen in Unreal Engine, and it lives alongside all of the other systems that simulate your runtime world in the first place. So Chaos can be triggered, it can be queried, and it can actually send events to the other systems as well and can interact with that. And that creates some incredibly tight integration between all of the systems. You know all of the things which are going on in Unreal, because all of the gameplay systems can can like really tightly integrate. And this was important to us because Chaos is so cool because it is a messy system, right? Like, you never quite know how the next destruction is going to happen. That is cool. That's part of the satisfying, experience. But it does make it unpredictable. And because nothing ever plays out the same, especially if the player adds some uncertainty into it, you need to make sure as a designer, if you're creating this as an interactive experience, that you have tools to actually deal with that. So Chaos lets you create runtime systems like AI, etc., that can account for all of that chaos because they can interact with the destruction after the fact. So I'm going to give you some examples of how that is actually can happen. And like when we're really talking about creating completely interactive experiences, maybe you can hook up afterwards. This is a topic we could talk about for a while. But some simple examples of what we did in the demo. To kind of demonstrate how you can interact with Chaos. The super simple one is actually a kill field. So one of the issues you might again have with a completely pre-baked like static vertex cache is that once you rain that down on part of the playing field, that part is off limits, right? Because you've just blocked it off and you can't do anything about it anymore. AI couldn't navigate through it anymore. If you accidentally block an exit, the player won't be exit anymore. So it's very feasible to just create a simple kill field, rain down destruction on that entire street right there, but then create kill fields that only crumble the specific parts of that area that you need to crumble. You can also create AI that actually shoots that up. So you can pretty much sanitize the part of the playing field that you're interested in and make sure that the action can continue in a runtime environment. So, we come back to chaos never being static. That destruction isn't static, so it's never this all or nothing proposition. You either completely clutter it up and then it's off limits or not. Now, of course, as we're talking about systems, AI is one of the big ones that we immediately think about, because when we're creating interactive experience, we have autonomous agents, right? We have AI, like enemies that actually want to interact with, that we want to interact with and shoot at, and they need to be able to navigate all of that. So we've done a lot of heavy plumbing there already and made sure there's support for chaos when it comes to AI systems. Nav mesh is fully supported on geometry collections. So in this example, it's actually a static mesh in here at the bottom, and that has nav mesh, and then we have geometry collections on the top. And AI can navigate on that, and they can do everything that you expect an AI to do. You could actually create dynamic nav mesh, which could be modified by debris. Now, you're going to have some performance implications there, but if you wanted to have that bridge destroy and have piles of debris invalidate nav mesh down at the bottom, and then AI can navigate around it, that's totally possible. We didn't actually do this for our demo because we didn't need it. We created something like a snowplow or cow catcher, I think is what Jeff, our lead engineer, called it, where AI could walk and kick away some of the debris to make sure that they don't collide with it correctly. But you can dream, big if you really want to think about using this in a game or something that is truly interactive, because the AI can query all of this destruction. So they might be able to use a large chunk of debris as dynamic cover, for example. And you can create like a really cool cover shooter out of it, something along those lines. Then AI, of course, needs to react to the destruction as well. This is really where these kind of systems come alive, when you have a robot standing in the scene and they're reacting to all the destruction that's happening around them, right? So again, we put this in the demo to make sure that some of this support is already there. So the first thing you're going to think about, of course, is that you want to use destruction as a tool to, kill people. And these are some early examples of when we actually brought this online. So every chaos destruction event is going to give you information about what the debris actually is and how much mass it has. And so then you can trigger appropriate effects. If it's big enough, you're going to trigger death, like right here. If it's small enough, you might just play a flinch or hit react, where the AI reacts to stuff hitting it but doesn't die. You can, of course, take this a little bit further, because you also get a location where these hit events actually happen. You're going to hear a little bit later of how you can actually filter and make sure you're not getting information overload from all the destruction happening around you. In this case, we can play flinch event, and jump to the side because of where the destruction actually happens. And then, of course, if something happens above, we can play the appropriate reaction there as well. So if you are thinking about using this in an interactive experience or even making a game around this, this is how AI can start really integrating with chaos in the first place. So these are autonomous AI agents. As a designer, I want to be able to work with chaos as well and have some tools so I can actually get events and act on those as well. So I want to give you some examples here. One of them is just, how do I detect damage and how do I react to a pillar, for example, getting shot up, which is what happens a lot in these kind of demos, in this demo specifically. So we created a little blueprint which we called a destruction detector, and it was listening to how much damage has been dealt to a specific geometry collection that we put inside that volume. Could have listened to everything everywhere, but I'm very specifically interested in what's happening to this pillar, right? And then I can subscribe to that, and I can create an event. And I can say, for example, if this specific pillar is getting destroyed, trigger an event and move on. So all of the demo progression that you see in our playable demo is gated that way. You actually see that happening. I'm shooting a specific pillar, and enough damage has been dealt, and then we're moving on. Now, instead of just listening to damage dealt to a geometry collection, I could also look at the mass, and I could detect how much debris has fallen and how much a pillar has been destroyed along those lines. This is the blueprint that we're actually using here. So you can see we're getting a chaos break event, and I can act on that. And I get information like the location, but I can also get mass. So if I wanted to create something like fill a container with enough debris, and there's a scale or something like that, and then I want to act when that entire container has been filled, this is how I could do it. And I can also integrate that back with what the AI is doing, right? Like what I want to do in these kind of games or interactive experience in the first place is have AI react to it. So if I want to invalidate cover, I can tie those together and say, you know what, this is valid cover until it's been destroyed to a certain degree, and after that, move on. You actually see Chaos do that a lot. Whenever she's zooming around in the first section, it usually happens because I smashed up one of those pillars and I invalidate cover that way. So this hopefully, especially if you're a gameplay programmer, you've done this, gives you a good idea of the heavy plumbing is there. Like Chaos as a system can fully communicate with the gameplay systems, and it can go both ways, and you can start building things around that. I have one final piece of information before I hand it off, and because this is a question that everybody's going to have and we probably get asked, and that's networking. This is a big topic, and there are more qualified people to talk about it. What I'll tell you as a designer looking forward is that Chaos is built with networking in mind because it's going to be our primary physics system of the future. And what I like about Epic is that we're a production company. We make these tools to make our own games, and you know what kind of games we make, and then we also hand them off to you. So if you look at the kind of games that we're making, we're certainly thinking about networking, and we're going to make sure that Chaos is supported in the kind of experience that we create, and I think also the kind of experience that you're creating. So with that, I'm going to hand it off, because I think we should hear a little bit more about how you actually make stuff look good and what's happening under the hood. So I'm going to give it to Jim Van Allen.
Thanks, Matt. Thanks for coming out today, guys. So I'm excited to talk to you today about the art side of the Chaos demo. We had a really talented team on this project, and I can tell you, it's been a lot of fun playing with this system over the past few months. So I was putting this presentation together. Sorry, I have to adjust the thing here. And I started to ask myself, as an artist, what do I really want from a destruction system? And here's what I want. I want to take random geometry, fracture it into a random pattern, allow a random user to hit it with random forces in random locations, and control exactly how it looks. So to boil it all down, it all revolves around one key word: control. This is what I really want. I want something that looks like total chaos to you, but behaves exactly like I want it to, runs in real time, and maybe meets the design or the needs of our design, environment, art, and engineering teams. So for me, everything in the system revolves around this one concept. And all that starts here with a new type of asset that we're calling geometry collections. Geometry collections are built specifically for destruction in Unreal. And Mike's going to give you more detail in a few minutes, but here's some key points if you're an artist. Geometry collections can be built from one or more static meshes, including those gathered together in blueprints or even nested blueprints. Geometry collections let you choose what to simulate, and they offer incredible flexibility in terms of how you organize and author your destruction. Once we have our geometry collection, we need to break it into pieces. Aside from a few items that were hand-modeled into large chunks, every piece of geometry in the Chaos demo is fractured in Unreal. And just as an aside there, we were allowed to use anything we want. We could have used offline tools or whatever. But it just, being able to fracture in Editor was just made the whole process so much easier. And it's awesome. So we can fracture each part individually, and we can apply one pattern across multiple pieces. We have standard Voronoi fracture, but we also have a suite of options that let you dial in a specific look. You can do radial fractures, clustered Voronoi, planar cutting with noise, whatever you need to get the most natural results. In a budget-conscious environment, we do subfracturing, which lets an artist control where to add complexity. Each time you subfracture, an extra level is added to the geometry collection. The Chaos system keeps track of each subsequent level, and stores that information into something that an artist can control, which we call a cluster. Now here's an example of a mesh where each fracture level is combined into its own set of clusters. These are a bit different from other systems in that the chaos solver treats each node like a single object until enough strain is applied to cause a break. So when we're simulating level 1 here, the system is only calculating those pieces. Conversely, if we turn off clustering, every single leaf node falls. Not super efficient, but it also doesn't look great. By tweaking our cluster strength values, we can therefore get a result that looks good and performs as optimally as possible. If you're like me and you're too disorganized, or I call it artistic, to meticulously keep track of each fracture and its cluster level, we have an awesome tool that lets you flatten the hierarchy and procedurally set up your clusters for you. And this allows you to effectively spam fracture an entire building and sort it out after the fact. You can reduce a really complex fracture to 5 or 10 objects if you need to. And because you can have as many levels as you need, you can explicitly control the density of each level. Which lets you control how, oh, sorry, lost my track there. Controlling how difficult it is to break each level is one of those wonderful times when performance and art requirements align and make something awesome. The next concept we need to discuss is the connection graph. Now, this is a lightweight connectivity map that is a bit different, a bit of a different paradigm for destruction. Here we have a few statically anchored pieces, but everything else in the scene, it has the potential to be dynamic. Rather than swapping from kinematic to dynamic like many other systems, our system applies strain, which in turn breaks the connections and chaos ensues. Now, we found this to be a great way to maximize interactivity while still retaining control over the amount of active rigid bodies. Okay, so we have everything set up. We see how it works. How do we interact with it? We do that with fields. Fields are the way that artists can directly interact with and control simulations. Fields can be used to control any attribute on any part of your geometry collection. You want to vary your mass, make something static, make the corner more breakable than the middle, apply some force. All of this is controlled with fields. Fields are created and controlled through blueprints. And in this example, we're applying some strain followed by a bit of linear force. Radial fall-off volumes control where the strain and the force is applied. Because this is a modular system, you can stack fields together, use noise multipliers, and do just about anything you can imagine. This example is the basis for a weapon field that runs on impact and can be expanded to do sticky bombs, high-caliber weapons, and rockets. Next, I'll show you 3 specific field types that we used. Anchor fields, they anchor things. They do exactly what you think. They lock the nodes in place. And in this level, we used anchor fields to lock the top and bottom of the pillars and walls just to control how much things collapse. These fields are often the base upon which everything else is built. And this is a fun one. It's a strain decay field. And this applies strain to the geometry collection. With enough strain, you break connections and the pieces fall. One of the really cool features of this system is that the strain required to break each cluster can be tuned by the artist. So this allows you to specifically tune your simulation for aesthetic quality, gameplay interactivity, or performance as needed. In this example, the strain field is being animated upwards and applying some force. The box underneath is a culling field that keeps it from getting crazy and reapplying the strain over and over again. It's a lot of fun to play with. And finally, this is a sleep field. It's pretty straightforward. They put things to sleep. But it's a really powerful tool. And here's a video to illustrate what's going on. Nope. Oh, yes. Yes, it is. Good. Didn't know if that was going to work. Sorry. Any object that moves below a predetermined velocity is put to sleep. Sleeping objects can wake up and start simulating again if they're hit by a weapon. Aesthetically, this keeps pieces from rolling around like crazy and being distracting. And finally, it gives you a direct performance throttle over a large area. As you can see here, I can completely destroy this gameplay area without any noticeable drop in performance. And finally, we're going to talk about caching. With caching, high-fidelity simulations can be pre-cached and played back in real time, resulting in a kinematic geometry collection. This means that you'll be able to author large-scale destruction events and still allow interactivity with the player and the environment. And that's my overview. I hope it gives you an idea of how artists can control just about every aspect of the chaos system. I can't wait to see what kind of crazy destruction you guys create with this. And now here's Mike Lentine, our lead physics programmer, to talk about the technical side.
Hello, thanks, Jim. So I'm Michael, and I run our physics team at Epic. And so when we set out to create a new physics and destruction system, we first wanted to figure out why we were doing this. And so we had two primary goals. The first was to give the power to our content creators, like Jim and Matthias, to generate the results that you've been seeing throughout the course of this talk and in our demo. The other is we wanted our system to be scalable. And this means effectively two different things. So we want to be able to create a single setup that goes all the way from a phone-powered device all the way to kind of a high-end PC. We also want to be able to continue to scale as we get more and more computational power over time to hundreds of thousands or millions of objects. So in order to do this, we had to develop a number of different techniques that I'm going to go through. So the first one is non-convex collisions. So as you create sort of polygon soup and you start fracturing it, you're not going to come up with every object being convex. And so the traditional ways of dealing with this are either to collide against the mesh itself, which gets really expensive, or to use convex combination approximations. Unfortunately, those can get expensive depending on how many convexes you have. And if you have too little or too few number of convexes, then you get a pretty poor approximation of the actual object. And you can't get desired behavior that you see kind of here in this example. So what we did is we came up with a completely different collision representation that allowed us to create fractured pieces that were art-directed, accurate, and fast. So you've heard a little bit about fields, and we did use them a good amount in sort of the demo, which this video is from. The primary ones that we've talked about thus far are things like strain or force application in order to break up buildings. But fields in general are a much more powerful concept than that. They're really just an object that you can place into a scene that essentially give you control over any property of the physics simulation. So for example, if you wanted to take the ground here and change the friction based on certain areas, you could take a box field, put it down over your ground, and then make that part slippier or stickier for your physics simulation. So this is an example that's much simpler than the one Jim showed that I'm going to go through in a little bit more detail that we used in our demo. So the first node you can see on the left is a radial fall-off field. So basically it just has a value and then starts falling off as you get further and further away from that point in space that you specify. We then add essentially some random noise to it, and we have a number of different nodes for how you apply noise. And then we combine those two with a culling field that basically turns that radial field into a sphere, adds the noise into it, and then we apply that, in this case, as a torque application every time essentially the weapon is shot in our demo. So we've talked about how Unreal is tightly integrated with chaos, and this is extremely important for things like destruction when it comes to various different other systems in the game, such as Niagara, audio, and gameplay events. So the two primary events that we utilized in our demo are collision and braking events. So collision events happen every time two objects collide, which is pretty intuitive. Braking events are somewhat similar, except they happen when an object essentially breaks apart from the building. So one thing that Matt touched on earlier is this can get unwieldy pretty quickly. So when you're making destruction, you expect to see a good amount of like smoke and dust. But if you were to spawn particles every time you hit a collision or a braking event, your screen would just be inundated with huge amounts of smoke and you wouldn't be able to see anything. So we provide a number of different filter mechanisms to try to reduce that. So for instance, for smoke and dust, what we did is we essentially created a grid. We essentially hashed the various events kind of into that grid and then spawned, say, one particle system for each cell in that grid to reduce the amount of dust and smoke that you end up getting. Another example is for audio. You don't necessarily want every single event to generate a sound. So what we did is we basically took all the events, we sorted by mass, and the ones that were heaviest essentially generated sounds whenever destruction occurred. And this gives us a way so you can hear all kind of the big events, but you don't hear kind of all the noise at the same time. And then, of course, for gameplay, Matt went over kind of how we use that to create reactions from characters. So a big component of this system we mentioned before is scalability. And caching is one way to achieve scalability, but we really wanted to make every part of the chaos system interactive. And so the system we came up with was essentially an interactive caching system. So the way this effectively works is you record your sim in Unreal using the same tools as we talked about. It'll run at, say, 5 frames per second, maybe 1 frame per second, however, depending on however complex a scene you want to do. It'll record that simulation. It will then essentially, there are a number of different ways you can use to play it back, but one way to get sort of the max of interactivity is you will register essentially all those objects with the physics system. They'll effectively be sleeping while they're playing back the cache, so they have very, very little cost. But they'll be set up, and so if any of them collide with something that's simulatable or interact with a character or anything like that, they can go active. And so you can have, in this scene, I think we had 300,000 or 400,000 objects through this cache playback. And if we were to start kind of interacting with these objects, then we could be maybe simulating a few hundred, but still have kind of that scale of 400,000 objects being used as part of your instruction and not have to pay the cost of doing so. So another thing we did, which was fairly important, but a little bit under the hood, is we redid the way that physics talks to the engine from a threading perspective. So this is optional, but right now, sort of if you download Unreal Engine 4.22 or before, physics runs as part of the game thread. And this is a fairly simple model, but it doesn't give you a lot of control as to how physics kind of interacts with gameplay. So one of the things we did was completely decouple that so we can have a completely separate physics thread. And this gives us a number of different cool features. So one is the ability to set whatever time step you want for a physics tick. So if you want to do a fixed time step, which is important for things like networking situations, then it's very easy to do so. If you want to run physics at a super high tick rate compared to your gameplay for very accurate interactivity, if you're not running a huge number of objects, you can do that as well. If you want to have highly interactive gameplay and a lot of physics simulating, but you don't necessarily need it to run quite as fast as gameplay. So if you're taking gameplay at 60 hertz, you can take physics at 30 hertz and get twice the amount of computational power than you would traditionally in the engine. So we covered upon geometry collections a couple of times. So what exactly is a geometry collection? So it's an actor representation that we use for rendering a destructible object. It's somewhere between sort of the static mesh and the skeletal mesh representations inside the engine. So the static mesh is just a way to represent a single object which can be transformed through space. If we were to try to represent this many pieces via a sequence of static meshes, the cost of the overhead of static meshes would get far too large for that to be useful. Typically, the way to avoid that is to use skeletal meshes, which give you the concept of different bones with different transforms on a single representation, which helps with the rendering cost overhead. However, there's a number of limitations with that system. One, there's a lot more overhead we need with skeletal meshes than we need with destruction because it supports all sorts of animation tools like linear blend skinning. It also has fairly low limits in terms of the number of bones you can simulate. So if you tried to use this to try to represent this building with skeletal meshes, you'd still need probably 100 or something skeletal meshes to represent it. So a geometry collection is essentially a representation where you can have basically as many bones as you want, similar to a skeletal mesh, where it doesn't support any type of skinning essentially other than rigid skinning, which is all we need for this kind of simulation. And because it's low cost with low overhead, we can have hundreds of thousand objects in these. And from a rendering standpoint, that means that essentially we can pay one draw call cost per material for something like this, despite the fact that it's breaking up into thousands of pieces. One of the things we've kind of been harping on a little bit over and over is that everything's an engine. And I'm not going to go through fracture tools too much, but the really important point that we want to convey is the ability to iterate and the ability to see your results and not have to go in and out of external packages. And that makes a really powerful tool for everyone. So Jim touched upon levels. And so what levels is effectively our destructible LOD system. So this isn't LODs from a traditional geometric sense, which is, of course, depending on how far you weigh, you're essentially rendering a different representation. This essentially determines how much computational power you're going to spend on your destruction simulation, depending on how much you specify is available. So if you have a piece of geometry where you break it up into 10 pieces, each one of those pieces is 10 more pieces, and so on and so forth, what you can do on, say, your low-end platforms is say, I'm not going to want to break up any more than the very first level. And then you're only going to have 10 pieces or so, but you'll never have the problem of needing to simulate way more pieces than you have the computational power available to do so. The other thing it gives you is scalability. So as you break it up, you're only ever considering sort of the level underneath the level that's currently simulating. So even on a high-end platform where you want to be able to simulate a fairly large amount of destruction, this entire scene is broken up into hundreds of thousands of pieces, but we're only really ever considering the 10 or so for each of these pillars at any given time until they break up further. And finally, Jim kind of touched on this as well, but it gives you some cool looking effects. So we can do things like shoot the bottom and the top off of these pillars, get kind of the entire center of the pillar falling, and then further break that up through forces and strains. So the last thing I wanted to talk about was dynamic strain evaluation. So as we want to scale larger and larger pieces of destruction in buildings, we need a way to author how these things break up without putting a huge amount of work kind of on our artists to do everything kind of manually. So we talked a little bit about the connection graph. And so what the connection graph is from a strain evaluation standpoint is each of those nodes in the connection graph represent an object. And each of the edges that connect those nodes essentially have an allowable amount of strain. And that strain can be set with fields or a number of other ways that we kind of provide in the engine. And then as we apply forces or decay strain or whatever have you, those connections essentially break. And this also helps us get an amount of kind of cool realism with it, because if you essentially break off like a corner of a building, you'll essentially get that entire corner falling, like you saw with kind of the pillars example before. So when you put all these things together, we can do quite a bit of simulation. So this was sort of a much heavier modification, but gives you the sense of just how much destruction kind of was put into sort of the level that we created, and how many bodies we can kind of push through this system, all running kind of in real time. So here we just basically apply a huge amount of force, and basically everything that we touch just kind of crumbles pretty instantaneously. But at the same time, all of this stuff was created in engine via our artists, and this was all running in real time. All right, so now I'd like to hand it over to my colleague Jeff from Intel, who's going to talk a little bit about making chaos faster.
Hey, I'm Jeff Rous. I'm at Intel, Senior Developer Relations Engineer. I'll talk to you about making chaos faster. So at some point, you've got all of those systems simulating, like Michael just showed in the last video, and you have to do all of that on the CPU. So what we did is we worked with Epic to optimize the low-level solvers, the data structures, and improve the thread parallelism to make things even faster. So what are the key learnings here is we learned that C++ is bad at SIMD. In performance critical areas, we integrated a tool called Intel ISPC and saw roughly 3x gains over the existing scalar systems. And so that was great. So now you can have even more things simulating at the same time. On on the data structure side of things, we found a bottleneck in T-set. And since if you know Unreal at all, that's a hash container. We were finding that that was a bottleneck when we were doing duplicate removal in intersection testing. So switch that to T-array, remove and swap, and great. Now we're up and running again. Also, Parallel 4 can be overused. Some oversubscription is good, but you don't want to go overboard. If you've got thousands of jobs going on at the same time, or tens of thousands, sometimes you can get into a situation where the thread start, or the work start overhead becomes too much, and it's actually faster to run it on a single thread. Batching is helpful here, especially if your data access patterns are cache friendly. So what is this ISPC thing that I was saying? So CPUs since the early 2000s have vector units that programmers can use to speed up their code. This is known as single instruction, multiple data, and you can do 8 floating point adds in one instruction, for example. We use this a lot in the chaos system to make it faster. One of the problems is that with C++, it's hard to get to the compiler to vectorize anything. So usual solution is to use compiler intrinsics that you then have to update with new instruction sets. So if you're working on PC, you also have to write those for ARM or any other platform that you want to support. This is where the ISPC compiler comes in because you can write it once and it can work anywhere. So ISPC gives you implicit parallelism in a language that looks like a shader language that runs on the CPU. And like a shader language, it assumes SIMD by default. And it looks a lot like GPU shaders in the way that they're executed. A big benefit, like I said, is you can write ISPC once, compile it to many instruction sets, SSE, AVX, AVX2, even ARM. It works on PC, console, Linux, Mac. If you're compiling for multiple instruction sets, there's an auto dispatch mechanism where it chooses the right CPU instruction set, the best one that your users supports. And you don't have to worry about doing compiler intrinsics anymore. We made good use of this in Chaos. And you can use it in your projects too. All you have to do is include a module in your build CS, add ISPC files, include the generated header that comes out of that, and Unreal Build Tool will handle the rest, including generating all of the different instruction sets, handles the linking of the object files, and you're up and running, hopefully faster than you were before. All of this was done to make it as seamless as possible for Unreal developers and, of course, the Chaos system that makes good use of it. So what is it good for? It's good for dense compute-bound workloads like Chaos. Heavy math, like physics intersection testing, cloth, CPU vertex transformation. It's best with contiguous memory. So when you're doing load, manipulate, and store, like if you're working with a T-array of data. It works best when there's no data dependencies between operations, and very useful when combined with Parallel 4 and a batching mechanism. So if you remember, I said it acted a lot like GPU shaders. They do, with some differences. Whereas GPU shaders all run to completion independently, with ISPC, each lane, SIMD lane, runs one instruction of the program. The difference lies in that ISPC runs in lockstep, so all of those SIMD lanes run all at the same time. And so they're guaranteed to converge at the end. So when you have branches in your code, you'll run the true, and then you'll run the false, and that's faster than it sounds, but you get convergence at the end there. One of the nice things that this gives you is the ability to do reductions across SIMD lanes. For example, if you're trying to find the sum of an array of integers, that's very fast. We use that quite a lot. The bottom picture gives you an example of what ISPC looks like. This is a RGB to gray simple function. And what we have here is convert n values using 3 multiplies and 2 adds. And with AVX, when you're running 8 wide, you can do 8 of those at a time. 2 of those operations can be fused into FMA instructions, so you're going even faster. And this function is roughly 8 times faster than the scalar implementation without needing to use intrinsics, and it remains readable. It works on everywhere that Unreal does. So that's a bit about what Intel did to help optimize the Chaos demo. Look for ISPC changes in 4.23 that are rolling out along with Chaos. And we have an ISPC talk if you're interested in hearing more tomorrow. Big thanks to my co-presenters, who I'll invite back up on the stage. Thank you.